Okay, let's talk about the unit circle and radians today. So, sorry, here's my pen. Oh, okay. First, let's talk about the unit circle. So we dealt with this. I mean, yesterday's lesson was all about circles. So, what is a unit circle? A unit circle is a circle with radius of 1, and we're going to need 1 unit. 1 inch, 1 centimeter, but 1 unit. And so we're going to use the unit circle to take trigonometry up to the next level. Today we're going to talk about radians, and then the next lesson we're going to go back and do the right angle trigonometry that you're used to, like SOHCAHTOA, but then we want to take it up to the next level. So let's just talk about the unit circle. So we drew the unit circle on our axes, and the idea was we kind of drew in a central angle. And the initial started here on the non-negative x-axis, and we rotated around. So the idea is that there seemed to be like a point. So if we drew the other way, we spoke about the subtended angle, like this arc. We talked about the subtended arc. So it looked like this angle with this rotation, kind of like cut off a specific arc. Okay, but the point is that the idea is that on the unit circle, each angle corresponds to a specific place on the unit circle. So like if we talk about a rotation of like 60 degrees, we can say that's like right here. That's 60 degrees. If I asked you to identify on the unit circle a rotation of 90 degrees, you would say, oh, Mr. Adler, it's right here, as if like it moved around to 90 degrees. So this is like 90 degrees on the unit circle. I might say, 225. And you would say, okay, Mr. Adler, it's kind of like right here is 225. That's the idea. So our rotations are now corresponding to points on the unit circle. In an exercise that you're going to do, you're going to be asked to identify 90 minus theta on the unit circle, and so the idea is you draw your unit circle. You're starting at, and also, assume that theta is acute. And so you'd be like, okay, well, the first rotation is 90 degrees, so I'm right here, but then I'm subtracting theta. So this is 90 minus theta. That's the idea. I might say identify, let me use another color. I might ask you to identify 180 plus theta. And you would say, no big deal. This is a rotation of 180. And there's a little bit more here. So this point here denotes like the rotation of 180 degrees. So instead of looking at the actual angle, we're actually moving along the unit circle. Here's a challenging one. How about negative theta? Where is negative theta located? Well, you say, oh, you know what? Negative in geometry just means direction. So in this case, I'm going clockwise theta. So although it's equal to a rotation counterclockwise, the negative says go clockwise theta. And this is where negative theta is located. Okay, let's move on. So let's talk about this idea of radians. Let's talk about this idea of radian and what's wrong with just measuring angles in degrees. What's wrong with 90 degrees, 180 degrees? What do we need something else for? Well, there's a couple of problems. First of all, if we think about, we want a function, right? And, well, we'll talk about that later. Here's the big problem. So, let's see. Let me erase this. Good. Okay. So, radians. What's wrong with degrees? Well, let's take our unit circle, right? And let's talk about a quarter rotation. This is a quarter rotation. And we call it like 90 degrees, right? Or a full rotation is 360 degrees. Well, the problem is we don't kind of know where they got that number from. We have some ideas of where the Babylonians got it from, but like it's not really like, we're mathematicians, we need something a little more than like, well, this is what they use 360. Don't get me wrong, I love 360. It's a great number. It's better than 100. But it's just, that's not mathematical. So what we're going to do is we're going to notice that every rotation seems to correspond to a unique arc length. Right? If you think about that, then a 90-degree rotation corresponds to a quarter of the circle, nothing else. A 180, so let me write that down. So, yeah. And so, you know, it's like 180 degrees corresponds to the semicircle. 60 degrees corresponds to 1/6. So there's this direct one-to-one correspondence. So we're going to use that. So we're on the unit circle. Right? We're on the unit circle. So we know that r equals 1, and therefore the circumference equals 2 pi. So 90 degrees seems to correspond to 2 pi over 4, or pi over 2. And 180 degrees corresponds to 2 pi over 2, or pi. My pen's running out of ink. Let's try another pen. What else? What does 270 correspond to? 270 degrees corresponds to 3 pi over 4. No, sorry, 3 pi over 2, because, well, yeah. And 360 corresponds to 2 pi. Right? So what we're going to see is that 180 degrees is equal to pi radians. That's the idea. So this is the connection. 180 degrees is pi radians. We have a couple of things to talk about here. There's a couple of things we have to clear this up. But this is just, once again, this is your conversion. Now, the relationship between degrees and radians is linear. So the relationship is linear. So if 180 is pi, that means 90 is pi over 2. And if 90 is pi over 2, that means 45 is pi over 4. And if 90 is pi over 2, that means 30 is pi over 6. And if 30 is pi over 6, that means 60 is 2 pi over 6, or pi over 3. And so this is really cool. So what we can do, we can continue to, so therefore, what I want you to do is go back to, I think I handed out the sheet where they gave you like this big column and you filled out sine, cosine, and tangent of 36, 45, 60, and all the angle. I think I gave that to my HL kids. But what we can do is start to, we can make a table. So we're going to start with 0, and we're going to go through the special angles. Let's see. 0 is 0. So this is degrees, and this is radians. 0, 30, 45, 60, 90, 120, 135, 150, 180, 210, 225, 240, 270, 300, 315, 330, 360. What we're going to talk about, so let's figure this out. Why are these important? Because every single one of these angles are multiples of 30, 45, 60, and 90. Which is perfect. So let's start to fill this chart in. We said that 180 is pi radians. If 180 is pi, 90 is pi over 2. If 180 is pi, 30 is pi over 6. If 180 is pi, 45 is pi over 4. And if 180, what do you think? If 180 is pi, then 60 is pi over 3. Let's continue. If 60 is pi over 3, 120 is 2 pi over 3. If 45 is pi over 4, 135 is 3 pi over 4. If 45 is pi over 4, 1, 2, 3, 4, it takes us back to pi. That means 225 is 5 pi over 4. That means the 315 is, well, let's think about this. Pi over 4, 2, 3, 4, 5, 6, 7. 360, 8 pi over 4, or 2 pi. So, because 180 is pi, 360 is 2 pi. 150, well, 150 is 5 times 30. 210, well, 7 times 30, 7 times 3 is 21, 7 pi over 6. Excuse me. 240, what do you think? Well, that's 4 times 60, 4 pi over 3. 270, that's 3 90s, 3 pi over 2. 300 is 10 30s, 5 pi over 6, which is 5 pi over 3. 300 is 10 30s, but 300 is also 5 60s, 5 pi over 3. 330 is 10. Let's see, what is 330? What is 330? That's 10. No, 330 is 11. 30 is 11 pi over 6. So, you're expected to know how to go back and forth between degrees and radians. Now, let's see. So, what's the conversion? Well, let's see. The way I first present it is degrees is to radians as 180 is to pi. If you set up this ratio, you're fine. But the books show a different way. But let's do 2 examples. How about we say 18 degrees? Convert 18 degrees to radians. So, if we use my method, we say 18 over radians is equal to 180 over pi. So, we have 180r equals 18 pi, or r is equal to, I'm sorry, there's a mistake somewhere right here. It's 18 pi over 180, which is equal to pi over 10. But some of you might say, hey, Mr. Adler, some of you might be saying, hey, Mr. Adler, can't we just take the degrees and multiply by pi over 180? The answer is yes. So to go from degrees to radians, multiply by pi over 180 degrees. That's what the books say. Some of you have learned this before. Once again, to go from degrees to radians, multiply by pi over 180. Can we go the other way? Absolutely. can we go the other way? Let's see. Absolutely. Let's see. How about pi over 5? Convert, sorry, I don't want to use blue. Convert pi over 5 radians to degrees. Do we write radians next to pi over 5? That's a thing we have to talk about. We kind of have to talk about it. To degrees, fine. So you say fine. Degrees over pi divided by 5 is equal to 180 over pi. Because it's a ratio. Corresponding, because it's a linear relationship, it's a direct variation. So we can set this up. So we're like, fine, pi d equals 180 pi divided by 5. And so we have d equals pi over 5 times 180 divided by pi. Well, this gives us 36. But some of you may have noticed, hey, Mr. Adler, why don't we just, if you want me to go from radians to degrees, why don't you just have me multiply by 180 over pi? And that's another quick technique. Once again, to go from degrees to radians, multiply by pi over 180. To go from radians to degrees, multiply by 180 over pi. It's your call. Personally, I like setting it the ratio, but I'm not looking over your shoulder. Now, there's an issue. First, well, it's not a problem. We don't have problems in this class. And the answer is 36. So you get this fun. If you think about it, like, pi divided by 10 is 18. Pi divided by, so therefore, pi divided by, multiply that by 2, and we get pi over 5 gives us 36, which means 2 pi over 5 is 72. 4 pi over 5 is 144. I mean, all these things come together. If I add on another 36, 5 pi over 5, 144 plus 36, this is pi, this is 180. So it all comes together. It all comes together. Okay, next issue. Well, everything we've been doing, this whole thing, has come off the unit circle. So the question is, does it always have to be a unit circle? And the answer is no. So let's explore that a little bit and come up with a better definition of what radians is. As I said before, we have an issue where we're writing pi radians. This is an issue, but we'll explore that, why it's an issue in a second. So let me erase this. Let me do it for time. Good. Okay, so does this hold for all circles? Because, the question is, does it hold for all circles? And the answer is, yeah. So let's take a look at a couple of circles. Let's take a look at circle number 1, whose radius, the first radius is 2. So we're interested in this arc length. Let's take a look at another circle. This radius is 5, and so obviously we're interested in this arc length. And our last circle is a much bigger circle. This one has a radius of 12, and we're also interested in this arc length. Because once again, we said that well, these are right angles, and we said that our claim is that the central angle uniquely corresponds to a specific arc length. And that was for the unit circle. And we got the connection of pi to 180. Let's see if we can get that same connection here of pi, or in this case, let's see if we can get the connection of pi over 90 degrees corresponding to pi over 2. So we go through the motions, right? So the circumference here, we know the circumference is 2 pi r, so this circumference, 1 is pi r, therefore arc length of 1 is, pi, because it's 1/4 of the whole circumference. Fine. Well, we don't have pi over 2, so this can be a problem. Let's see what's happening other places. So we look at the second circumference, the radius is 5, which means the circumference is 10 pi, and therefore this arc length, S2, this is 2.5 pi. 10 divided by 4, 5 over 2, 2.5. It's not looking too good. But let's try something else. The third circumference is, the radius is 12 in the third circle, so the circumference is 24 pi, and that means S arc length 3 is 6 pi. And so you're like, Mr. Rowley, where is the pi over 2? Wait, that was supposed to be, well, if you notice that in all three cases, S divided by R is always equal to pi over 2, right? So we have pi divided by 2. Over here we have 2.5 pi over 5, and we have 6 pi over 12. They all equal each other. So now we have a better definition of radians. The radian is, in any circle, the ratio between the central angle, the radius, and so theta in radians is equal to the ratio of the arc length and divided by the radius. That's the idea. You have an angle, you have a central angle that subtends an arc in a circle of radius r. We're going to call the measurement of that angle is the ratio of the arc length and the radius. So, fun fact, 1 radian is equal to basically in the circle where you have the arc length is equal to the radius. This is 1 radian. And you can actually figure that out. It actually is about 57.2 degrees. So 57.2 is 1 radians. That's the idea. Are you going to be asked that? No, but it's a fun fact. And so how are we doing for time? Perfect. So we can quickly do some problems and we can clean up something. So for example, you got any circle, here's example 1, you got a circle, here's the radius is 5, the arc length is this angle in a circle whose radius is 5 subtends an arc of length 8. The question is, what is this angle in radians? And you're like, fine, theta equals h over 5 or 1.4 radians. I could ask you another question, but it all comes down to, what is my next question? Oh, let me change this, sorry. These all come down to, you got a circle, you put a central angle in here, you have a rotation. Can you see the board? Yeah. For example, let's see, this is equal to 2. The radius is 6. What's the arc length? You're like, fine. 2 equals s over 6, x equals 12. Now, and then, this is kind of cool. Then, this is great. We can take the formula we came up with in the last class. Right? Because remember, I asked you to find, actually this saves you a lot of time. This first one is, so we have this formula, theta equals s over r. In the last class, I asked you to find the area of the sector. And we said, okay, given a radius and an s, we know it's 1/2 s, s times r. Because I joked, I said, oh, it's like 1/2 the base times the height. Well, in the world of radians, and I'm going to say this a lot, you're in the world of radians, knowing that theta is equal to s over r, if I just multiply r, r here, but then I put an r down there, I can rewrite this as 1/2 theta of r, and that is the area of a sector. But once again, you have to be in the world of radians. You can't put 60 degrees in there. It has to be in the form of a radian. Okay. Two things. First of all, I think the book uses L. The book, and I think IB uses L for arc length. Some books use S. I think L for arc length. So the formula is theta over L over R. Or, L equals R theta. Or in this case, second, what's the second issue? I'm waiting. The issue is exactly what are the units of radians? Because, we make this big stink about, oh, Mr. Riley, you forgot the units. Is it centimeters? Is it feet? Is it miles? Is it kilometers? And so, what are the units of radians? And so this is kind of odd. There are no units. Radians is unitless. Radians are unitless. They have no unit. Like there's just it's you just write. So I have a circle here. Let's think about this for a second. What does that mean? It has no units. Everything has a unit. Radians, and there's some other things in science that just don't have units. Let's think about this for a second. We said that the radian, that measurement is based on the ratio of arc length. So let's call this, I don't know, like 5 inches, right? And the radius is 3 inches. And we have this formula, theta equals 5 inches over 3 inches. Well, mathematically, these cancel out. So we say theta is 5 over 3. We'd say radians on the side, but there's no units. There's no inches. There's no degrees. It has no units. That's not really important. But, sometimes you'll see, so if theta equals 2, that's a correct answer. If you're nervous, like I get sometimes, you can write radians. You'll see it. But just know they have no units. It's kind of an interesting topic. Talk to your science teachers. They'll tell you other things, other measurements that don't have units. And that's basically it. Good luck.